Massachusetts, and the title is Néron-Severi Groups and the Specialization.
Okay, thank you very much. And I'd like to thank the organizers of the program for I had a very nice stay here during the last month. And I'd especially like to thank Min-Young Kim for explaining to me, spending several hours explaining to me his program in Diophantine geometry over the past few weeks. All right. So this is joint work with Devesh Maulik and Claire Voisin. And this talk is going to be about how the Néron-Severi group varies in a family of varieties over a field such as Q bar. And so to start with, well, I know that most of you probably know what Néron-Severi groups are, but let me just start with this. So I'll be working over an algebraically closed field, K, and when I'll only take Néron-Severi groups I'll only define it for smooth projective varieties. Actually, you could work with proper varieties if you like, but let me just, for simplicity, let me stick to projective varieties. So then there's an exact sequence involving the Picard group. So the point is to classify the subvarieties of codimension 1, and those are the irreducible ones are the irreducible divisors, and they generate the Picard group. And inside the Picard group, you have the subgroup of consisting of divisors algebraically equivalent to 0. And then the Néron-Severi group is, by definition, the quotient of these. And it's known that this group is isomorphic to the k points of some abelian variety. It's essentially the continuous part of the Picard group, and then the quotient is some finitely generated abelian group. If you're thinking about the Picard group as being the points of the Picard scheme, then this is the connected component, and this is the group of components. No, not necessarily. In here, yes, but it doesn't. I'm talking about the groups here, so it doesn't make a difference. I'm just okay. So you can understand this in another way if k is the complex numbers from the exponential sequence of sheaves on the associated analytic space. So this is the sheaf of holomorphic functions and the sheaf of units, the invertible functions. So you have this on the associated analytic space. And from now on, I'll probably drop that, and it'll be clear. If I write h2x comma z, you know that that's not supposed to be Zariski cohomology. OK. So if you have, OK, so from the exponential sequence, OK, so maybe I should put it, well, there really should be maybe a 2 pi I somewhere here. But OK, let me not worry about that. All right, so this sequence, if you take cohomology, it yields the following. If I, well, OK, let me. So as I said, all these are supposed to be analytic. All right, so, and then, well, OK, the next one is, let me write as the kernel of the map from H2. And then this goes to 0. All right, and what I want to say is that this sequence here, in this case, in the case of the complex numbers, is the same as this sequence. And this just follows from various comparison theorems, so Gaga and other things. OK. So so I'll want to use this later on. And there's another way of thinking about this. This is the this is the 0-2 part in the Hodge decomposition, and so its complex conjugate would be the 2-0 part. So this kernel is the same as the classes in here that map into the 1-1, the 1-1 classes. So this is also the set of Hodge classes in this case. And the fact that this is the same as this is somehow the content of the Lefschetz 1-1 theorem, which is going to come up later on. All right, so, all right. So I know that. All right, and now the rho of x I'll define to be the rank of the Néron-Severi group. So this is called the Picard number of the variety. So now I'm back on to arbitrary algebraically closed field. And this, this varies in a complicated way. And just to give you an example, I mean, it's somehow, it's almost like an arithmetic quantity. So in fact, it's very, for certain kinds of varieties, it's closely related to Mordell-Weil ranks in sort of in a function field case. So here's an example. Suppose I start with an elliptic curve. Then one can show, so using facts about abelian varieties, that if you take E cross E, then the Néron-Severi rank, the Picard number, is equal to 2 plus the rank of the endomorphism ring of E. And so this is a number in the set 3, 4, 6. I mean, essentially the idea is you have E cross E, and you have, inside E cross E, you have E cross 0, and you have 0 cross E. And then for any endomorphism, you get the graph of the endomorphism. And that gives you extra classes. So you always have the diagonal and maybe extra ones. But the point now, but now if you imagine E varying in a family, this number is going to vary in a complicated way. It's not constant on an open subset of the base or anything because I mean it'll depend on whether E has complex multiplication, and it'll change on a countable union of varieties in the base. All right, so now let me talk about, in general, the Néron-Severi group in families. So okay, now from now on I will restrict to characteristic 0. So characteristic 0. And now, so by family I'll mean I have a base that's an irreducible K variety. And then I'll have, this will be a smooth projective morphism. All right, so then you have the, well, I have the generic point of B. So let me call the generic point eta. So this is just spec of the function field. And I can also take the geometric generic point. So let's see, where did, okay. All right, so the geometric generic point, which is the same, well, I'll just put a bar over things. So choose an algebraic closure and then define that. And that's just because I always want to be talking about Néron-Severi groups of varieties over algebraically closed fields. And okay, and then I can also take any closed point of the base, so B, which is just going to be a K point. And then you have the, well, for each of these points, you have a fiber of the family. And you can ask, how do the Néron-Severi groups compare? All right, so what we have in general is that you can make some choices that will lead to an injection of the general Néron-Severi group into the special one. So okay, so it depends on choices. I mean, naively, if you're thinking about if you think about the Néron-Severi group just of generated by divisors that are defined over the function field itself instead of the algebraic closure, then you can spread them out to divisors on the total space and then restrict to the fiber. And that's essentially what the definition of this map. And you have to do a little more work if you want to define it over algebraic closure. Okay, so anyway, so once you have this, it follows that this one is bigger. So the rank of the special fiber is at least, the Picard number of the special fiber is at least as large as the generic fiber. And so the question is then, how often do you have equality here? And what is the locus of points where equality fails? So let me define the jumping locus in the base to be the set of points where the Néron-Severi group actually grows. And you can show, well, okay, so, or the Picard number grows. Actually, you can show that the Picard number growing is equivalent to the Néron-Severi group growing. So okay, so anyway, so you have this locus where this number jumps. And in general, what you can show over any k is that this locus is a countable union of closed subvarieties. You can see that in this kind of example if you imagine a family of E cross E. Okay, so it's a countable of the base. And so, well, if k is the complex numbers, if the k is a field of complex numbers, then you know that a countable union of closed subvarieties cannot cover all the complex points just by measure theory or something like that. But if k is a field like Q bar, it could be that this countable union covers there are only countably many points altogether, so these could cover, in theory, they could cover all the points. So the question is, are there any k points that are actually generic in the sense that they have the same Néron-Severi rank? So, all right, so the main theorem then, our main theorem is that, at least under our hypothesis that the characteristic is 0, this jumping locus is not equal to this countable union does not cover all the k points. So there are always some, so even if k is Q bar, there are some points where the Néron-Severi group does not grow. Oh.
Is it easy to show that each enclosed subvariety is proper subvariety?
Oh, well, it's somehow, it's almost by definition. And I mean, well, yeah, yes, I guess so. I mean, because the points in each of these closed subvarieties, you could take not just k points, but any point over an algebraic closed field. In particular, you could take the geometric generic point. So if one of these subvarieties, well, it doesn't really make sense. I mean, it doesn't make sense to say that one of these, if one of these were equal to b, that would mean that the rank of the Néron-Severi group at the generic point was greater than itself. So, I mean, I guess, yeah. I mean, there's something to show here that it's actually that this union has. I mean, it's a non-trivial question what you ask, but it follows from the property of this countable union. Yes. Sorry? Oh, the rank of a finally generated abelian group is just so you just rank. So okay, so rank of a finally generated abelian group is defined to be the dimension of M tensor Q. So I mean, if M is going to be isomorphic to torsion, and the rank, that's the rank. Can this I mean, in general, usually, I mean, typically this is not contained in any single closed subvariable. Actually, I'll give an example in a second, but let me mention that in this, there have been special cases of this that go back almost 30 years. So there's work of Shioda in 1981, and then Terasoma, 1985. Actually, what I'm going to give is a special case of some of this. Okay, so special case of. So here's an example of what they proved. They looked at I guess Shioda looked at surfaces in P3, and Terasoma looked more at complete intersections. So if you fix some degrees and you exclude some values, so it's exclude other than 3 or 2 or 2 comma 2, then there exists smooth complete intersection so of x of so over q bar of hypersurfaces of these degrees di such so this is going to be a surface, so and then this is such that the Picard number is what you get generically, namely so such that the Picard number is 1, and you can get that from this theorem by looking at the family of all such complete intersections, and you can show that the generic Picard number is 1 in that family under if you exclude these values. I mean, I want to exclude things like a cubic surface, for which you know that Néron-Severi group is not just Z. Okay, all right. So let me go back to this example though, the E cross E family. So let me imagine that so what I mean by a family of E cross E. So now to make sense of that, I'll start with a family of elliptic curves. So all right. So if I start with a non-isotrivial family of elliptic curves, over some base, so E over B, and if I take my family X to be the fiber product of the fiber square over B, so then the fibers of this are the squares of the fibers of this family, then by what I told you here, the jumping locus is a set of points of the base above which the fiber of the elliptic curve above there has CM. And this is, if you're working over the complex numbers, this will always be dense in the complex topology, just because if you look in the upper half plane, the quadratic imaginary numbers are dense in the upper half plane. So it's pretty, so you're not going to be able to prove this theorem by finding a little hole in the complex points of the base where there's no jumping, and then say, oh, there are going to be some q bar points in there. You can't do it that way. All right. Another thing you can see from this is that it's necessary in this theorem to require characteristic 0, because if you did the same example over FP bar, then all the fibers would have complex multiplication. Because every elliptic curve over FP bar has complex multiplication, although the generic fiber would still have no complex multiplication. So this would be an example where this countable union covers all the points, all the k points. So there's something about q bar making q bar is somehow bigger than FP bar, so from the point of view of this kind of theorem. No, it doesn't. It doesn't really matter. I mean, yes. Yes, you can shrink B if you want. You can. Yes, that's a corollary of this. Yeah. In fact, I'm going to now state some other refinements that are even stronger than this. So I want to say in what sense. I want to say in two different senses. I'll prove that this is a small set. So for two different definitions of small. All right. And they'll correspond. There will actually be two proofs of this theorem, two completely different proofs, and they'll prove that it's small in two different senses. yeah, well, maybe I should write this so main theorem over FP bar is false. Okay. All right. So I'm going to have to use some property of Q bar that FP bar does not have. All right. All right. So let me. Sorry. Was there a question? All right. So let me state two refinements of the main theorem. So the first one is going to be a p-adic statement. So, sorry, let me start with the field of p-adic numbers, take an algebraic closure and the completion. So this is CP, and this is a evaluation ring. The field with evaluation, and I take the evaluation ring inside. So the first refinement, which I call theorem 1, is that if you have a smooth projective family over a base which is an irreducible, separated, finite type R scheme, then if you look at the R points of the base, so which are going to be some subset of the QP points, it's essentially they're essentially the points where, well, they're points for which the fibers have good reduction in this. So this, you can talk about the jumping locus inside there. And the statement is that this jumping locus, that now, if you look at the R points of B, it's unlike what happens over the complex numbers. There are actually lots of holes where there's no jumping. So, and in fact, this set of, in fact, the holes cover the whole space. So this subset, this jumping locus, is p-adically nowhere dense. So not only is it not dense, but it's nowhere dense in the set of R points of the base, which, as I said, is there's going to be some open subset of the CP points, open in the p-adic topology. Yes, I mean, but you'll want to apply this in situations where it's not, yes, where it's not empty in order to get something interesting from it. But if you start with a family over Q bar, it will be defined over some ring of integers of some number field, and then or some ring of S integers of some number field, and then you can embed that embed such a ring into ZP. And so on. So if you have this theorem 1, it's quite standard to deduce the main theorem from this. So, sorry, what do you say? It doesn't really matter. It does. So it can be. I mean, it. If B is projective, then there's no difference. But I mean, if you start with a family over an affine base, then there might not be a way you might not be able to spread it out to a family over a projective space and keep the fibers smooth and projective. So it's stronger if you allow all arbitrary varieties. So okay, so all right, so I'm just writing down what I said, that if B is over Q bar, then you can you can use the fact that the Q bar points in any variety form a subset that is p-adically dense in the CP points. So this means that this theorem implies that you can, so if you have any holes in the CP points, you can find QP bar points. Sorry, if you have holes in this set where there's no jumping, you can find a Q bar point inside the hole. And so this theorem implies the main theorem, at least over Q bar, and with a little more work, you can do it over any. It's not you can do it over any. In fact, you can get over any algebraic closed field using some of any field of characteristic, any algebraic closed field of characteristic 0. All right, so before showing you the proof, let me state the second version.
To be sure, the Néron-Severi group is unchanged after the algebraically closed base.
Yes, the Néron-Severi group will be unchanged under algebraic closed. Yeah, that's right. That's a general fact. I guess, I mean, there are various ways to see that. I mean, one way to think about it is that if you think about the Picard scheme, that if you make a base change, you just base change the Picard scheme, and the sort of connected components stay the same. So the Picard group grows only because the pic 0, the abelian variety, has more points over the bigger algebraic closed field. Okay. So the second strengthening of the main theorem is not p-adic. So this is more, I'll use Galois methods and Hodge theoretic methods for this. So for this, I will assume that K is the algebraic closure of some finitely generated field. So with F, a finitely generated field over Q. And I'll assume that everything that everything comes from varieties defined over F. So in X and B are over F. They come from varieties over F. So now I will define, if I have a subset, I want to say that it's small in some sense. So I'll introduce this word sparse to mean that. Well, let me write the definition and then explain it. It's something related to Hilbert irreducibility. So it's sparse if you can find another variety, a cover of B. So where this is so some cover where this is a dominant and generically finite. So dominant and generically finite morphism, and where the top one is also these are both irreducible. So okay, I should assume that this is irreducible. They're both irreducible varieties, and such that so S, well, such that for each point in S, so well, let's say, okay. Well, okay, let me say it this way. For each closed point of B associated to a point of S, so in other words, for each point of S viewed as a closed point, so for associated point to S, the inverse image, its pre-image under the fiber of this cover in this cover, is not a single closed point. So this is over. I'm thinking of these as being a morphism of F schemes. So it's some statement about some irreducibility of something. So let me give an example just to clarify what this means. It's very closely related to the notion of a thin set in the sense of Hilbert irreducibility. But I wanted to state it's something like the notion of thin set, except I wanted to have a notion for for points over an algebraically closed field. So, okay, so here's an example. So, all right, so I will take B to be the affine line, and B prime will also be the affine line, and my map will be the squaring map. Or okay, in that case, an example of a sparse set would be the set. So over Q, an F will be Q. So I'll take the points of Q bar. These are the points on the affine line over Q bar, such that as a number, B is not a square. Sorry, B is a square. B is a square in the field that it generates. Okay, so some funny condition, but most B's do not have this property. So this, yes, is it clear what I mean here? So, for example, 3 is an example of an. Oh no. 3 is not an example. But anyway, so 4 is an example. All right. All right. So this is an example of a sparse set. It's pretty rare for a number to be a square in its own number field. Okay.
But this does not imply that in a square, for example, there are elements of Q.
Yes?
Well,
That become squares in Q bar?
That are in this set, but that are not square in Q. Now, I just would like to understand the difference with K.
Oh, well, if you intersect one of these, if you intersect this with the ground field, then you get an example of a thing. If you take a sparse set and you intersect it with the ground field, and if you're working over an affine space, then you will get a thin set. And that improves in particular that a sparse set is not all of B of K in particular. So yeah, so anyway, so you can guess what the theorem now is. The theorem is going to be that in this setting, the jumping locus is sparse. And so then, as a consequence, if you combine this will imply the main theorem by using Hilbert irreducibility theorem. Okay? All right, any other questions about this before I go on to the proofs? All right, so let me start the proof of the p-adic case. Yes? I fix F, yes. Unfortunately, it actually does depend on the set. So I really should say sparse relative. If I wanted to be very precise, I should say sparse relative to F. And I should make the definition. I should put those words in the definition too.
But the statement is relative to any given F, so that we can choose F arbitrarily.
Yes, you can. Well, the theorem.
But B has to be defined.
Yes,
Yes.
of course.
Yes. So okay. But in any case, in order to prove the main theorem, you need it only for one F, and that will do it. So. All right. So let me begin the proof of theorem 1. So this is just to remind you, this is the statement that the jumping locus is not, that the jumping locus is nowhere dense p-adically. So let me first, just to explain why I work p-adically instead of over the complex numbers. Let me first do a proof that does not work. So all right. So over the complex numbers. Well, I guess I said things related to this already. But I want to explain in another way why you can't find holes in the complex points where there's no jumping. So, and this just goes back to the Lefschetz 1-1 theorem that I mentioned at the beginning. One way of characterizing the Picard number is as the dimension of the kernels of the map from H2. So I'm going to use rational classes now, just so I can talk about dimension. It's essentially the same, though. So there was this map in that exact sequence I had in the beginning, well, except that I've changed z to q. And so this is the map that goes from well, another way of thinking about it is it goes from H2xq into H2xc, and then this is a quotient of H2xc, and it's the quotient of H2xc by fill 1 in the Hodge filtration. So, okay, so this is a formula, and now the question is, now what happens as I vary x in a family? So let me put a b here to denote I'm taking the fiber in some family, and ask what happens as I vary b in a disk, in a little complex disk in the complex points. So these vector spaces, these form a local system. It's some local. I mean, I can trivialize it analytically. So just a family of vector spaces. So I can view this as a constant. And this also, this is a fiber in some vector bundle. This you can also trivialize, but these trivializations are not compatible, and the map between them with respect to these trivializations varies as you vary b. So this is all well known. So if you think of a fixed class here, but now you view the sort of this constant class as you vary b, and you look at its image here, then you get the image will vary holomorphically as a function on u. So you get a holomorphic function of the point, and then the question is, and then this will jump. This number will jump when one of these holomorphic functions has a 0 that wasn't there generically. So in other words, you get that the jumping locus, well, restricted to this open set, is restricted to this disk. So intersect u is just the union over the c's that are where they give you, well, over some of the c's of the zeros of these holomorphic functions in u. And well, I mean, some of these FCs might be identically 0. Those are the ones that give you generic elements of the Néron-Severi group, and then the other ones are, but most of them will, well, the other ones will give you non-zero, not identically 0 holomorphic functions. The question is, where do they vanish? And as you vary c, this is an additive function of c. So what you get here are a finite dimensional Q vector space. So these functions, they form a finite dimensional. So these form a finite dimensional Q vector space of holomorphic functions. And the problem is that this is bad because if you have a vector space of holomorphic functions and you look at their zeros, they will typically be dense. So for example, I mean, if it's just a simple example, if you think on the upper half plane, if you think about the functions 1, z, and z squared, and you take q linear combinations of those, or even z linear combinations, and you ask what are the zeros of quadratic polynomials with integer coefficients in the upper half plane, that's going to be dense. So okay, so this is not a good proof. So you will not find any holes in the jumping locus over the complex numbers. So so the idea is to repeat this proof over the p-adic numbers. So now what does this mean? I mean, you can't use the exponential sequence does not work as in the usual way, but there is a substitute for the Lefschetz 1-1 theorem. So okay, I'm not going to be able to give all the details, but let me just say that there is a Berthelot and August proved a p-adic Lefschetz 1-1 theorem And this gives an analogous formula for the Néron-Severi rank. Namely, it shows that if you restrict attention to a residue disk, so in this setting, if I choose a point of B over the residue field and look at the set of points that reduce to that. So for B in a residue disk in U in B of R. Well, okay. I mean, there's some. Technically, they work with finite extensions of QP, but you can generalize it. All right. So you get a formula for the Picard number, namely that it's the dimension of a kernel. Okay. Now this doesn't make sense anymore. We don't have Betty cohomology for the p-adic setting, but the substitute here is the crystalline cohomology. So you take the crystalline cohomology, and the point is that the crystalline cohomology is something defined for a variety in characteristic P. And so you define it for the fiber above the reduction of B, and the reduction of B is something that's constant in this residue disk. So it's just something that's constant. It's going to be the substitute for the rational classes. So okay, and I'll just let me work over CP. So let me just tensor that with CP. And this crystalline cohomology is, by various comparison theorems, it's isomorphic to the de Rham cohomology of the fiber in characteristic 0. And then this thing, which is the analog of H2x comma C. And then this thing is a quotient of it. It's the quotient by the Phil1 in the Hodge filtration. So this is going to be, so the analog to right here is, okay, so H2 de Rham of the fiber, and I'll do it over, so let's say over CP, and then to get something analogous to that, I take the quotient by Phil1. So the kernel of these are sort of the analog of the Hodge classes. And then their theorem says that the kernel of this is well, okay, so is spanned as a CP by the classes of algebraic cycles. So no, there's nothing, no. Yes, in fact, you don't even need to go up to CP for that. In fact, it's really just, you could do this. In fact, the actual theorem is you work over a finite extension of a Witt ring of some perfect field, and then you have this. Sorry, is there a question?
I have to think just over QP because I am confused by CP. And I was thinking that a class could be algebraic about if it is in reduction it is algebraic, and if it is in the good level of the filtrate.
If it, yeah, that's the.
The reduction, I need that it could be a good eigenvalue of Frobenius.
Sorry, I'm taking. Sorry, I should be taking the classes here. I'm sorry, I wrote this incorrectly. I meant, okay, so what I should be writing are the images. Sorry, but I mean the. You're right. What I want to take here are the images of the span of the algebraic classes. In this space here. So the point. Okay. So when I say algebraic classes, I mean line bundles on this reduction, which is the reduction is independent. The reduction is independent of within this residue disk. And so I start with only the algebraic classes that are in here. Okay, so maybe this is a little confusing now, because I want to write, okay, so let's say Q classes, and then take the dimension of the Q vector space here. You're right. The theorem says that if you start with a line bundle on the special fiber, and you want to know whether you can lift it to a line bundle on the generic fiber, And the condition is that when you take its crystalline class and you take it across the comparison isomorphism, it should lie in the fill one. And that's a necessary condition, just because the class of an algebraic cycle always lands in the de Rham cohomology, always lands in the fill one. And the crystalline class and the de Rham class the crystalline class map and the de Rham class map are compatible. So it's necessary for it to lie in fill one. And what their theorem says that that's necessary and sufficient. And so it gives you a criterion for whether for these things, for these classes on the special fiber to come from classes on the generic fiber.
Now you don't need to take the tensor with CP.
Yes, I guess I don't need to
Q
take
or
this.
QP.
So maybe I should just, yeah. Well, it's not just QP because it might be it'll need to be the Witt ring of the residue field
Yes, the
tensor.
tensor Q maybe. Tensor Q. So you would like to, so this is usually over bit ring, so the tensor Q.
Tensor. Oh, you mean okay? If this is over, I see what you mean. Yes, that's right. So if this is going to be something over the Witt ring of the residue field, and then tensoring Q, you can work over that field if you want. Okay. So all right. Okay, so this is supposed to be analogous to this formula, and then what this tells you, with a little more work, is that this jumping locus inside this residue disk, U, is again a union of the zeros. So it's well, sorry, it's a union. I shouldn't say over X. It is in the algebraic. I don't have a good note. Okay. Well, let's just say the algebraic class is in here. Of the zeros of power series. So if I choose local parameters for on this residue disk, then these are going to be the zeros of power series FC on this U. And again, this will be some fine dimensional. Well, these classes will form some finely generated abelian group, and then these will form. These zeros will be some finely generated. Well, you can work over Q. You can take a fine dimensional Q vector space of p-adic power series. So it's completely analogous to this one. So you can view this as then being a union over the non-zero elements of some fine dimensional vector space of power series. So where this dimension of, maybe I should write this on the board. So where you can, in fact, you can, well, maybe I could say you can contain. You can work with a QP vector space if you want to, and take where this is some fine dimensional QP vector space, and then there's the miracle of p-adic analysis, some peculiar lemma. That's somehow unique to p-adic in the p-adic setting. That such a union is p-adically nowhere dense. So you don't need to use any properties of this vector of these power series. Just any fine dimensional vector space of convergent power series on a disk, on a polydisk. The zeros will be p-adically nowhere dense. And so well, I mean, obviously I haven't explained the details, but that's how the proof
And
goes.
that's where you don't want to be over QP, but over a big enough extent.
For this, yes, because Right. We don't know how to prove that over QP that you have a statement like this. I mean, if you have if you're taking a union of, if you're really taking a union over QP,
Yes.
then of course you can take zero. You can find a family vector space where the zeros cover all the QP points. So, but the fact that you have a lot of room inside CP. CP is somehow infinite dimensional over QP. It's unlike the complex numbers being two-dimensional over the real numbers. You have enough room that even these countable unions, it's as if you're taking countable unions of things of infinite codimension. So there's still some hope that you can find some holes. All right. All right, so let me, okay, so any questions about this?
So can you replace the CP by the periodic completion of any infinite extension of QP?
Yes, in fact, in our paper, that's what we write. You can do work with any. You can start with any discrete valuation ring with perfect residue field and do something similar. Yeah, I should say. Yeah, our paper is, by the way, you can find it on our. It's finished. You can find it on our website if you want. All right, so let me now. Okay, so let me now say a few words about the other proof. So the other proof is Hodge theoretic and uses the monodromy actions. So this was the theorem that the set of the jumping locus is sparse in the points over this finally in the algebraic closure of the finally generated field. So in this one, I use the analytic. So I choose an embedding of f into c, or f bar into c even, and I look at the Betty cohomology, and on this of any fiber, and on this you have an action of the monodromy group, so the topological monodromy group. So this acts on this space, and you can look at the classes in H2 that are invariant under this action, or that are not quite invariant. You can look at the classes whose orbit is finite. So it's invariant under an open subgroup of the monodromy. So this is I'll call these the essentially invariant classes, and then you can, if you want to, you can replace. I mean, this is all happening inside a finite dimensional vector space. So there's going to be some subspace, and you can replace B by a finite. You can make these classes actually invariant just by passing from B to some finite étale cover. So I'll replace B by a finite étale cover. To assume that H is actually invariant, is pi 1 invariant. So the things that are invariant under a finite index subgroup are actually invariant. All right, so then a theorem of Deligne says that this subspace of the cohomology of the fiber is exactly the image of the H2 of some smooth compactification of the total space. So this is the global invariant cycle theorem. So of the total space. It's the image of the restriction map to this fiber. So restriction. And this morphism is a morphism of Hodge structures So its image is going to be a sub-Hodge structure in here, and you can, and these are all polarized if you choose an embedding of projective space. So you can decompose all these Hodge structures. And so in particular, you can write things in the following way. You can take x bar q and decompose it into the kernel of this map plus its orthogonal complement. And for the fiber, you can decompose it into the image and its orthogonal complement. And then this restriction map is going to be an isomorphism between these pieces, and 0 here. And yeah. So this shows various things. Okay, so you get this isomorphism here. So this is all as polarized Hodge structures. So this shows in particular that this H, which a priori depended on B, is independent of B because it's coming from this global thing. And all right, so and now if I want to understand the Néron-Severi group, I need to look at the Hodge classes. I want to look at the Hodge classes in here and how they vary as B varies. Sorry, is this blocking your view? No? It's okay? All right. Okay. Okay, so, all right, so now, so therefore, I have, okay, so I want to find the algebraic classes. I want to find the algebraic classes in this Hodge structure, and so I'll look at the two pieces separately. So first, I have the dimension of the algebraic classes. So I'll be working over Q. So in H. So by the Lefschetz-1-1 theorem, that's going to be the same as the dimension of the space of Hodge classes in H. But I just said that H is independent of B. So this part is independent of B. And so in particular, these classes are going to be classes that come from the generic Néron-Severi group, of the Néron-Severi group of the generic fiber. Oh, independent of B. Okay. Yeah, okay, so independent. And on the other hand, now let me look at, so it suffices to now look at the classes in the other piece. So the dimension of the algebraic classes in the H perp. And this can be bounded by, well, if I tensor with QL, then this is isomorphic. This by comparison is isomorphic to the L-adic homology, and then you can look at the Tate classes, the ones that are invariant by an open subgroup in the Galois group. And then this, and now you can use a variant of a lemma of Terrasoma. So by some variant of Terrasoma lemma, you can show that this is 0 for most B, for B outside a sparse subset. And this is some sort of, so this, the way you prove this lemma here is, well, okay, I'm essentially out. So you use the fact that you compare the Galois action to the monodromy action. So it goes into that last statement so the proof of this is the fact that the image of the Galois action of the field of definition of your point. So B is now an F bar point on the variety. And you look at how it acts on the L-adic cohomology, which I'm on this sort of motivic piece here. So, and you take, and then what you prove using some sort of L-adic version of some infinite Hilbert irreducibility theorem, which follows from the classical Hilbert irreducibility theorem, that this contains the image of the topological monodromy. So. And because of that, and because H perp had no fixed vectors, you can prove that there are no fixed vectors by this Galois group either. So all right, so I'm out of time. I was going to mention, so maybe I'll just mention one thing, that you can try to generalize these to higher codimension cycles instead of Néron-Severi group, which is about divisors. You can look at higher. You can look at the image of algebraic cycles of higher codimension in the cohomology, and look at how the rank of that, or the rank of that space varies in a family. And the proofs almost work, except there's some very important ingredients that are missing. So in the p-adic approach, well, let me start with the other one first. In this approach, there's the use of a Lefschetz 1-1 theorem here, and if you want to do the analogous thing, you need a Hodge theorem, or you need a Hodge conjecture, or at least a variational Hodge conjecture, or something like that. And if I had that, then I wouldn't be talking about this. And in the other approach, I used the Berthelot-August Lefschetz 1-1 theorem, the p-adic Lefschetz, and that has not been generalized to higher codimension either. That there is a conjectural version of that due to Emerton, but it's unknown. And the only thing we can say about all we can say about those two conjectures, besides the fact that we have no idea how to prove them, is that the p-adic Lefschetz 1-1 theorem applies the complex variational Hodge conjecture, but that's not very useful, I guess. All right, thank you for your attention.
So any comments or questions?
So in the case when one knows that odd is to say absolutely odd, then the statement would work in the sense of absolutely odd, like for abelian variety.
Oh yes, in fact, yes, you have an application of this to, you're right, there's an application of this to algebraic varieties. For example, you can prove, this is actually an older theorem, I think, due to, it's paid by Rutger Note, that if you have a family of abelian varieties, you can look at the locus where the endomorphism ring jumps, and then that will be, you can prove that locus is p-adically nowhere dense and also and sparse. So that's a sample application. And actually, you can deduce that from these theorems. Yeah, that's essentially divisors again.
But
yes.
you can also use higher really odd classes. It's kind of exotic.
Yeah. Okay. I'll talk to you about it afterwards. So.
Knowing that we find a point where the rank of the Néron-Severi group is the same, one could go further and ask, one can find a point where the Néron-Severi group is exactly the same.
Yes, it turns out that when the ranks are at least in characteristic 0, this specialization map, the co-kernel of the specialization map of this injection the co-kernel is always torsion free. So the condition that the rank does not jump is exactly the same as saying that the Néron-Severi groups are actually equal.
That would apply for cycles in a higher dimension.
Okay, so
Is there some arithmetic analog? Do you think? I mean, of course, not if the residue fields are finer, but maybe somehow, where you mix the characteristics. I mean,
an arithmetic analog of which
where the base is maybe
of the main theorem.
Yeah.
Well, I don't know. I have to. Okay, I'll talk to you about it. I guess I haven't tried to think. I have not tried to think about that.
Are the refinements 1 and 2 independent?
Well, they look very independent. I mean, one is completely p-adic, and here's one thing I can say, that we have these two notions of small. One is that you can apply them to subsets of B of Q bar, and you can ask, is one stronger than the other? And the answer is no. We can find examples that are p-adically nowhere dense, but not sparse, and we can find examples that are sparse, but not p-adically nowhere dense. So that shows that neither proof dominates the other one. So in that sense, that's a definite answer to your question. That the answer is no, that they are actually different.
What do you mean precisely by you find examples of what?
Of a variety over Q bar, and a subset of the points.
so let's have the speaker again.